In this video, we are going to start investigating characteristics and applications of fluids. First thing to say about fluids is that they are not necessarily liquids. This is not a state of matter in the sense that a solid, liquid, and gas are states of matter. All of us in this course have had some sort of chemistry, either high school or at the college level, where you have talked about states of matter, solids, liquids, and gases. For our purposes here, fluids are both liquids and gases. We define a fluid in several different ways. Maybe it's better to say one characteristic of a fluid is that fluids yield to shearing forces. A shearing force is a force applied tangentially to a surface. Right? So think of friction on a solid surface. It supplies a tangential force, a force tangential to the surface. Something like water resistance or air resistance, although we think of them as frictional forces, act a little bit differently than, strictly speaking, kinetic and static friction. You have to be moving through those fluids to experience that force, but it doesn't even make any sense what moving through a solid would mean. You can't move through a solid, and that is actually why solids are able to respond and do not yield to shearing forces, whereas fluids do. Now, that doesn't mean that fluids can't produce forces. If you've ever done a belly flop in a swimming pool, you know that there are forces exerted from the fluids. But the upshot of it is all forces exerted by fluids are normal to a surface, right? When you did the belly flop into the water, the force that was supplied to your body was normal to the surface of the water. Of course, if you did your belly flop properly, that's right into your belly, and that's why, you were a legend in 3rd grade. Good job. So this is going to be really important as we go through talking about fluids. The reason they can't do this, I should point out, is because the intermolecular bonds are either very weak in the case of liquids or almost non-existent in the case of gases. Definitely non-existent in the ideal gases that we're going to look at, whereas a solid has really robust intermolecular bonds, and so it's harder to, or it's easier to respond to a force tangential to its surface. So that's what we're dealing with when we're talking about fluids, both liquids and gases. So the first thing we need to define, we've seen this a little bit before, is the idea of a density. And this is not only for liquids, gases. Solids also exhibit a certain density. We use the Greek letter rho for a volume density. We're going to define it as the mass of an object divided by that object's volume. So this is a capital V for volume. In situations where I have a capital V for volume and a lowercase v for velocity, I will usually do something like add a tail to my uppercase V so that you can distinguish them. I won't do that normally, but in cases where it's hard to distinguish, I'll try to do that. This is defined, in the case of, well, it's defined as mass per unit volume. Now, for solids have a definite volume. And liquids, at least to a good approximation, have a definite volume. I have to say good approximation. Actually, I have to say it for solids and liquids, because liquids can compress a little bit. Solids can actually compress a little bit too. It depends on the solid. But for the purposes of this course, we're going to consider both solids and liquids to have a definite volume. Of course, a solid can change shape and a liquid cannot, but they have a definite volume. And of course, the mass is a definite quantity. So what this turns into for solids and liquids is some sort of material identifier. Densities are material specific. If you were to look at a chart and look up the density, say, of aluminum, has a density of 2.70 times 10 to the third kilograms per cubic meter, right? That's our units, kilograms per cubic meter. Which means if you find an unknown substance and you're able to run some experiments on this and you determine that its density is 2.70 times 10 to the third kilograms per cubic meter, you have a really good chance that what you have is aluminum. Now, of course, that doesn't mean that there aren't other substances with this same density, but it does mean that if you have aluminum, it's got this density. That turns out to be really, really, really useful for us. So we call density an intrinsic property. Density is intrinsic. It is a property contained, or is a property possessed by a material just by virtue of being that material. Right? Mass is an intrinsic property. What's not intrinsic, though, is the mass of a particular sample of an object, right? Having mass is an intrinsic property. A particular mass is an extrinsic property based upon the density and the particular volume of your sample. So what that turns into, very often, we rearrange this definition for the mass. Mass is equal to rho times the volume, the density times the volume. So if you have a certain material and you can look up the density of that material on a chart, and then you can measure it and determine its volume, then you can actually determine the mass of your sample without having to put it on a triple beam balance or any sort of other scale. If you know the density from a chart, if you know what the material is, you can measure it and determine its volume. If you can measure it, I should say, and determine its volume, you can then determine the mass of that material just with this simple calculation. But that's density. Solids have a definite density. Liquids have a definite density. Gases, however, do not have a definite density. Gases expand to fill the container they are given. If you've ever bought a propane tank to go on a gas grill and you carry it home new, it's really heavy. But then you take it back to the store a month later after you've been grilling a lot, and it's pretty light. It's pretty light because all the gas is out of it, right? All the propane has been used up, and so it's now basically empty. But the volume of that container didn't change, right? And the gas inside that container fills the whole thing. And so because the volume of a gas can change, the density depends upon the container that you give it. So density for gases can be a little slippery. It cannot serve as an identifier without further qualifications. You know, the density of a certain gas at a certain temperature in this particular volume can serve as an identifier. But that's a lot of qualifiers to come through. So we're going to have to deal with that later when we start talking about gases specifically. All right, that's enough about density. The next thing we should talk about is something with which we have some practical experience, and that is the idea of pressure. I say we have some practical experience with it because all of you at this point in time have pressures in your body. Most of us have swum down to the bottom of a swimming pool at some point. Most of us have been on an airplane flight and felt the pressure in your ears change. And so we use this word. We kind of understand what this, or most of us kind of understand what this word means. But in this course, since it's a physics course, we've got to be more rigorous. So we're going to define pressure as a force exerted per unit area. Right? If I exert a force on something, I necessarily have to exert it over a certain area, if I push on this paper with my finger, right, whatever area of my finger is in contact with this paper, I can take the total force that I'm applying, divide it by that area, and come up with the pressure that I'm applying. This turns out to be really, really useful when we're talking about fluids. Air pressure is a thing which we have some familiarity with. Water pressure is a thing which we have some familiarity with. But it doesn't have to be those things. It doesn't have to be fluids. Pressure exists in a lot of places. One of the places that you might be surprised to find it is this. It's a normal pair of scissors here. I'm going to cut this paper, which I was just writing on. All right, this is one sheet from the last one. And I'm not pressing very hard at all on these scissors, and they cut right through. Why is that the case? Well, you know, there's lots of physics here. We can talk about the torque and the leverage that I'm exerting here. But here's the upshot of it. Let's see if I can get it to focus in. The edge of these things is actually, come on, focus. It's actually really, really small, right? And there's another really small edge over here. So the actual part of the scissors, that's in contact with the paper is a very, very, very small area. And so if I apply only a little bit of force, the denominator of this ratio turns out to be really, really tiny, right? And that causes the pressure to go through the roof. One of the demos that sometimes I do with students when we're in person is I will have them hold up their hand, and I will take my hand and I'll push on their hand, right? And I'll push reasonably hard, but then ask them, okay, does that hurt? And usually they say no, and I say, okay, well then let me push like this with the same amount of force. And it actually starts to hurt a little bit. It's not terrible, right? And then you ask them why. Well, the same amount of force exerted over a much smaller area turns out to be higher pressure, and we sense that. And then I ask them, okay, well, what if I were to pull out some sort of like sewing needle and do that same amount of pressure? Would you allow me to do that? And of course they all go, well, no, of course I wouldn't, because it would go right through my hand, because the area of the tip of a sewing needle is truly tiny. And the denominator here, the smaller it gets, the larger pressure you actually have. And what will happen is you'll exceed the design specifications of your skin, and that needle will just go right through. So that's the definition of pressure. I will say we do the same thing with this equation that we do with the density equation quite often. If I have a certain pressure exerted over a certain area, I get out of that a force just by rearranging this definition. I can determine a force if I know the certain amount of pressure that is being exerted on a certain area. Units of pressure are, from this, newtons per square meter, but we wrap that up in a Pascal after Blaise Pascal. So a Pascal is a newton per square meter. I don't know why we don't wrap up the units of density in something. Maybe you can become a famous physicist and name it after yourself, but we do call this a Pascal. You will see other units of pressure. Sometimes you'll see units of torr. Sometimes you'll see millimeters of mercury. We will actually talk about that one. Of course, you can, in this country, you'll probably see inches of mercury. We'll talk about that in future videos when we talk about barometers and how they work. But these are all units of pressure. In this, we're going to stick with the SI, which is the Pascal, which is a newton per square meter. All right. We will come back in the next video and talk more about pressure and how to calculate it and what it means.